Hi, hello. My name is Klaus Moelmer. I'm professor of physics at the University of Aarhus in Denmark. I'm working with quantum physics, and what I'm going to talk about for the next few minutes is some of the physics that we're doing, and I'm also going to talk about the way that we have been communicating with composers and choreographers and musicians on bringing some of the quantum world alive in music and in dance. Quantum physics is the description of the microscopic world. All around you, you see beautiful phenomena in nature. You see galaxies, you see flowers, you see waterfalls, rainbows. And a lot of this physics is all described by the same equations, the same concepts and ideas. But when we move down to the very microscopic scale, to the atoms, who after all is actually what makes up everything in our world around us, life is different. Things are different, reality is different. And that's what I would like to talk a little bit about. There's an interesting connection between the way I, as a theoretical physicist, describe the microscopic world and the way that we describe music and sound. So, quantum physics started in the beginning of the 20th century. It started around Niels Bohr, the Danish physicist, who constructed his model for atoms. Niels Bohr was facing a challenge to understand, why does neon light shine red? Why does the light on the highways shine orange? And why do we get very particular colors if we are heating up different kinds of material? Physicists had since the beginning of the 19th century been observing the light from stars and from the sun, and they have observed lots and lots of very characteristic colors, what we call frequencies in the optical spectrum. And all these colors were related to the emission of light or absorption of light by very particular atoms. So it came in handy that when we look at the colors of light from a star, we actually know which atoms are sending out those colors. Astronomers know exactly which materials form all the stars you can see in the sky. But nobody knew why. Why does the hydrogen atom shine with its particular colors? Why does neon light shine with the red color? And this is really what Niels Bohr was explaining in his model of the atom from 1913. Niels Bohr's model of the atom is taught in school. You may have heard about it. It says that there's an atomic nucleus, and around that nucleus, a little light particle, the electron, is oscillating. And Bohr, he postulated that it could only orbit in very particular distances, and therefore it could only orbit at very particular frequencies. And this would explain why the light has the very particular frequencies that we observe. Bohr's model was quite fantastic, but it only works very well for one kind of atoms, and that is hydrogen. Other atoms, like helium, like argon, the atoms that surround us in the air, do not really fit very well to the description of Bohr's model. And in the 1920s, people came up with a completely new description, which is called the quantum description. And this is where music enters in some funny way. Because if you take a music instrument, like a wind instrument, the clarinet, or a string instrument like the cello, then you know that it will emit sounds with very particular frequencies. The tone that we hear is a frequency of sound oscillating many hundred times per second. And every time you pitch a certain string on your violin or your cello, you get the same sound. You get the same basic tone, which is a particular frequency. So why does that happen? Well, it happens because the string can only vibrate in a very particular way. The string is an object which is fixed in the ends, my elbows, and then the string is going up and down, not as slow as I show you here, but hundreds and hundreds of times per second. And that will cause the particular phenomena that we call sound. And you know that that frequency is tied to the motion of the string. You can also see a more wiggly motion like a figure eight, and that is actually an overtone, which is just twice as fast as the sound you hear if you see this slow vibration up and down. And the string instrument player can also put down his finger on the string and actually force the string to be only able to move on one side, and that is known as the octave, or making this particular frequency. So why am I telling you about this? Well, that's because in the mid-1920s, physicists did not know why atoms only emit light at particular frequencies, but they knew very well that wind instruments and string instruments emit sound at particular frequencies. And they knew that the explanation was that you have this wavy motion. You don't have a particle which is moving around. You actually have an extended object who is doing this wave going up and down. So physicists, they said, maybe we should describe atoms not as particles but as waves. And we have a lot of mathematics for waves, and it was a very quick exercise for a physicist called Erwin Schrödinger to actually write down one of the mathematical equations for waves, solve it, and find out that he could get exactly the same frequencies as Bohr had obtained for the hydrogen atom. So Schrödinger's equation describes also the phenomenon of light emission with certain frequencies, but it does it in a fundamentally different way. The good thing is that Schrödinger's theory also applies to all other atoms. And physicists like me, we solve the Schrödinger equation to this very day and describe all phenomena in the microscopic world using essentially the same mathematical equation. And it's a strange equation because it is giving us a description of microscopic phenomena as if they are wave-like rather than particle-like. What we thought was an electron as a particle moving around the atomic nucleus is now a wavy phenomena which is penetrating space around the atomic nucleus. And all microscopic phenomena are no longer particles being particular places, but this kind of wavy objects which are all over the place. This raises philosophical questions because when we actually detect the particles, we still see a dot here or we see a dot here. And why is it then that you are described mathematically as a wave, but when we observe the particle, we actually see it as a small particle? Again, the Danish physicist Niels Bohr entered, and he offered the explanation that the wave theory is really just a description of our knowledge about the particles. The microscopic world is not a wave, it's also not a particle, it's a phenomenon that we observe, and the mathematics for describing that phenomenon is the mathematics of waves. And then when we observe the object, well, if we observe a particle property like here is the particle, then we see a point where the particle is actually identified. Very strange, very philosophical. Niels Bohr once said that it's interesting that everything we call real is made of something which is probably not real. So with this fantastic world, of course, I can talk for hours and hours about the quantum mechanics. And I have talked for hours and hours about quantum mechanics to my students. I've also talked for hours and hours about quantum mechanics to normal people in outreach talks. But I have particularly enjoyed in the past few years to talk for hours and hours about quantum mechanics with Kim Helveg and with choreographer Kalle Dora from the Royal Ballet in Copenhagen, and trying to explain what interests me and engages me in the strange physics of the microscopic world. And Kim Helveg has composed BEC music, which is music inspired by a quantum phenomenon called the Bose-Einstein condensate. He has written music for piano duo, which is playing themes from the quantum world. And some of the things we have been discussing has led to ideas for the music and also inspiration for the music. One of the things we have tried quite immediately to install was to actually play the music of the atoms. So atoms have very particular frequencies of light. It's not the same as the string of the violin or the string of the cello. So if you play a cello or you play a clarinet, then when you play a tone, you will have an overtone spectrum, which will typically contain the octave and the fifth and the quart, because they are the natural tones coming when you play these instruments. If you take a hydrogen atom, you get particular frequencies, and they have a different progression. It's not twice the frequency or 3 times the frequency that is played as higher tones on the atom. It's a different progression. Niels Bohr's formula was a mathematical formula who said what are these frequencies, and we have taken with Kim those frequencies and translated them from the optical visible frequencies down into the audible sound frequencies. And that gives you scales, and we have named them after the first experimentalist who discovered those light frequencies, but now they become musical scales on which you can actually compose music and you can play music on real instruments. So that's one level in which we have used the quantum world as a gimmick or as a creative limitation for which tones we were allowed to play, and that has then led to its own special kind of music. Other themes in the quantum world are also interesting to pursue in an artistic way. So the whole question about being a wave, being not clearly in one place or many places at the same time is something that we have been trying to discuss. What does it precisely mean? And in particular in the work with the choreographers and the dancers, they are in fact much better at doing wavy motion in front of their audience than I am in front of you. So it has been very exciting to talk to the choreographers and dancers and say, could you think about how would you reflect on and illustrate not being well localized and suddenly becoming well localized? If you have pairs of particles in the quantum world, they may be completely delocalized and at the same time strongly correlated with each other. This is called entanglement, and it's really a tight connectedness between particles, which is stronger than things we can see in the classical world. And again, of course, you can have a pair of dancers who can dance and they can be correlated in the motion they actually perform. It's a direct illustration of quantum phenomenon, but of course we're not doing this, we're not recruiting artists to do demonstration experiments for us, but we are rather saying, can you use this as creative material? With the compositions in the quantum movement, we have been looking more deep into the world of particle physics. And in the particle physics world, it's very exotic. It's actually the creation of the whole universe, where we started from nothing, and then out of that nothingness came particles. And the processes leading to creation of particles is a very exciting one. Formally, what can happen is that out of nothing you can have a particle and its antiparticle appear together. They can actually fly around independently, and then later they might go back and disappear and become nothing again. You think it sounds exotic? These antiparticles were discovered in the late 1920s, early 30s, and today we actually use such antiparticles. For example, in hospitals where you can get scanning based on antiparticles being created inside your brain, meeting a real particle, becoming nothing, but emitting light in the same process. And then when the machinery is detecting where the light arrives, you can very precisely see where are the blood vessels in your brain and if any damage has been taking place. A famous American physicist, Richard Feynman, invented drawings, little pictures, a little bit like small road signs, showing why this particle goes this way, this particle goes that way. Now two particles appear and then they disappear again. And making little drawings instead of writing equations. Just knowing that every time I make a drawing saying here's a particle crossing my screen like this, I actually mean that it could go like this, it could go like that, it could be a wave being all over the place. But mathematically that little drawing represents all of that physics at the same time. The same time, in the same way, creating a particle and its partner and removing them again means it could have happened at all. It could maybe not have happened, it could have happened 2 or 3 or 4 times, and it could also have happened somewhere else. And as a mathematician, you just have to do some mathematics to understand how that drawing is actually leading to a real calculation. Feynman's drawings are very nice because it organizes for our mind the microscopic physical processes. And I've been drawing a few of these sketches. I use them in my own professional world, but I've also made a few of these sketches and presented them to Kim, who has scanned them and put them in sheet music paper format. And then suddenly you can see how particle motion can become a tune, or you can think about the characteristic tune, the characteristic sound of these different processes. And again, not to illustrate what happens in the micro world, but maybe more to see, is this a new way to look at the time and space and understand how they can be represented in the music, which is not doing things in space, but is actually more doing things in time. I read over this last few months a book about Marcel Proust actually, but the author is making a big point about his novels trying to describe both paintings and music in extreme detail. And he's also using concepts from the painting to describe how music is formed, and he's describing how the music is actually present in paintings. And of course, famous painters like Kandinsky tried to put in rhythm into his paintings. So how do you make a picture who's static forever still reflect the rhythm in time that you have when you listen to music? And artists of different sorts have trying to put inspiration across between these different topics. I hope that with this project we can bring a scientist in as third partner or fourth partner together with artists in a way to have the physics, the ideas from the insights that we have about time and space to also inspire and influence the way that you can represent them artistically. For my part, I can say that I have been interacting with artists, I have been visiting conservatories, I have been giving talks to audiences where there are painters and writers, and I have noticed that the questions I get from these highly trained professionals are extremely exciting. They are not the same questions as I get from a physics audience. They are still questions with a deep knowledge, deep insight, and deep experience with aspects of the same world that I try to describe. So maybe we will not only hear quantum music, maybe the physicist like me will also be able to have an inner music that can inspire me to do better physics, more creative physics, new and out of the box type of physics.